welcome back. Welcome back to the last session of the Industry Day. In this session, we'll hear back from our program organizers. We'll start with the current program on computational complexity of statistical inference, and Guy Bresler from MIT will tell us about it.
Great, thanks, Prasad. Let me share my screen here. Hopefully this works. Whoops, we're somewhere in the middle. Okay, there we go. All right, excellent. All right, so yeah, it's great to tell everybody about the program that's actually ongoing. It's been, as far as I'm concerned, a glorious success so far, and I'm still very excited for the remaining half of the program. I guess here's the list of organizers who've co-organized this program along with me. And I'll tell you a little bit about the sort of high-level motivation and objectives of the program, of the sort of subfield that the program is focused on, and then a brief update on the activities that are ongoing. All right. Sort of the setting is of statistical estimation of various structured signals. This sort of question is like absolutely ubiquitous in all of science, engineering, statistics, data science, machine learning. On the right is sort of a picture from cryo-EM, which I guess recently won the Nobel Prize. And the idea is you're observing some noisy image, some noisy data that comes from a molecule, and you'd like to reconstruct the structure. Okay, so in general, you observe some data and you want to figure something out that you don't know. In the mathematical models for these problems, typically there's a bunch of parameters, for instance, dimension and sparsity, number of samples, and some signal strength parameter that determine the features of the model and determine whether it's easy or challenging to solve the problem. And at the high level, you should think of maybe dimension and sparsity as some sort of parameters governing the signal structure. There's some other parameters that govern the quality of the data. And so sort of with this in mind, the basic questions that a theoretician would like to understand are when can you and when can't you solve a statistical problem of interest as a function of the signal structure and the quality of the data, and how do these both together result in us being able to solve a problem or being unable to solve a problem. So of course, these questions are somewhat sort of basic and have been investigated in some sense for many, many decades. So on the one hand, the field of mathematical statistics for 120 years now has been interested in what are the fundamental limits on the amount of data that I need in order to solve some problem, but has had relatively little to say about how much computational resource does one need. At the same time, the field of computational complexity has largely been interested in precisely the question of how much computation do I need to solve some question. But those sorts of questions that have been studied aren't data problems. And so it turns out that actually these two resources have a beautiful interplay, and they together determine the amount of resource of each type together determines whether one can solve a problem or not. And in particular, there's a sort of trade-off between data resource and computational resource that appears in many problems of interest. So oftentimes, as one has more computational power, one needs less data or a weaker signal in order to solve a problem. So this program is really just focused on this phenomenon, which is quite ubiquitous and really sort of deep and fascinating from the intellectual standpoint. So I'll just give a very brief example of a problem that in some ways kickstarted the subfield. This is actually sort of maybe not coincidentally sort of started by Berthet and Rigollet. Philippe Rigollet is giving sort of the next 5-minute overview for the sister program. And so they were interested in what's the minimum signal strength in a problem called sparse PCA. And this diagram is what we call a feasibility diagram or a phase diagram. And what I'm going to draw, so on this axis, we have on the horizontal axis some structure parameter K. Turns out to be sparsity, but it doesn't really matter. On the vertical axis, we have a signal strength parameter. It's a stronger signal as we go down. And the point is, you would like to understand for every point, for every setting of the parameters, is this problem feasible or not? Okay, so they first answered this question in the information theoretic sense, in the sort of statistical limit sense. Here's the line, impossible in the purple region, possible in the white. Okay, now for a mathematical statistician, this is the end of the story, but they wanted to go a little deeper, and they were interested in efficient algorithms. And so they observed that the efficient algorithms that they knew achieved this smaller region and left the white region sort of undetermined. So it's not clear if there are efficient algorithms that can go right up until the information theoretic barrier. And so they really wanted to understand this, and they actually observed that it's computationally hard in a region that explains why these efficient algorithms are not achieving the information theoretic optimality. And this hardness was based on Planck leak, and they observed that in some sense there's Planck leak living inside of the sparse PCA problem. And so hardness of Planck leak explains hardness for sparse PCA. Now, this spurred a tremendous amount of work over the last decade. And here's maybe just a subset of the relevant references. And the point being that dozens of people spent a tremendous amount of effort to just understand this one lonely problem of sparse PCA. And I'd say at this point, there's a pretty good understanding of sparse PCA, but at the same time, there's dozens and dozens of other problems of interest, and one would like to understand those too. And so the aim of the program at the high level is to take a cue from computational complexity theory, where relationships between problems have been investigated, relationships between classes of algorithms have been investigated, and some mapping of the landscape has been achieved in order to simplify the picture. And so the aim is to do this sort of thing for statistical problems, to understand their complexity, both statistical and computational, and how these interplay with one another. All right, so I'll briefly just say that there have been several workshops which have been really terrific. There's one workshop left, which I'm very much looking forward to. There have been a bunch of program activities that are ongoing in any given week, working in reading groups with people trying to work on specific important questions, various seminars, long-form board talks, open problem sessions, lots and lots of activity, of course, beyond this, various collaborations and ad hoc meetings between people. And to conclude, I'll just say that it's really been tremendous to have people from various sub-communities that are interested in these questions from all across computer science, statistics, statistical physics, and areas, aside from this, information theories, probability, and so forth, all coming together and able to collaborate and discuss these questions. So I'll end there. Thanks.
Thank you, Guy. Any questions for Guy while Philippe sets up? Okay.
I don't see any percent.
Our next speaker is Philippe Rigollet from MIT, and he'll tell us about geometric methods in optimization and sampling.
Oh, Philippe, I think you're muted. We can't hear you, Philippe.
Yes, can you hear me now?
Yes, thank you.
Thank you. Apologies for that. All right. So there's actually quite a bit of topics that are involved, and what I'm going to do is illustrate the themes that we covered during this program through an example, which is related to sampling. All right. So if you know that there's been some huge advances in terms of sampling coming from deep neural network. There's this famous website that generates images of people that do not exist. But sampling beyond this impressive image generation is pervasive to many questions. In Bayesian statistics, obviously, we want to sample from posteriors, but also online algorithms where we want to have some mixed strategies, so game theoretic kind of questions. So in many places now, sampling has become a central paradigm in statistical questions, just like estimation or testing, for example. So let's start with a very vanilla example of this. So this is the Langevin Monte Carlo, Langevin diffusion. That's the basis of Langevin Monte Carlo for sampling, where the goal is to sample from a density pi, which is e to the minus of, say, a convex potential v. And it's very well known. It's almost a standard exercise to show that this stochastic differential equation that you see here, called the Langevin diffusion, has this distribution pi as a limiting stationary distribution. So a natural way to try to get samples from pi is to simply discretize this stochastic differential equation and get points that are happening quite late. There's some adjustments like metropolis adjustments that you could add, but this is actually a pretty robust and highly studied discretization of this diffusion. So let's take a closer look at this Langevin diffusion, and we're going to start seeing some parallel between sampling and optimization. So the first thing is, if you forgot about the Brown motion part of it, you are actually just following a gradient flow. So if I was just following this red part, I would simply try to minimize the function v by following the steepest descent method, which is just a continuous time gradient descent, also known as gradient flow. And so, that's already a connection. We know that it's basically a stochastic gradient descent version of this with this additional stochastic term. And what you have is essentially some trajectory on RD, and actually this point of view that merges optimization and sampling was instrumental in getting the first results on convergence of discretized Langevin algorithms. But the approach that's favored throughout this program, and that was the basis of the proposal that we submitted, was there's another connection to optimization, which is the following. So if you think about the curve of probability measures that tell you the law of xt at each given time t, so let's call this mu t. So it's a curve evolving in the space of probability measures, and you're trying to understand how this marginal distribution evolves. Well, this is actually well known, right? I write partial t of mu t, and it's a partial differential equation known as the Fokker-Planck partial differential equation. This is very well known. And this is a nice descriptive perspective. Actually, many analysts will talk about Fokker-Planck rather than Langevin. But really, what was instrumental in changing this point of view was this paper by Jordan, Kindler, and Otto in the late 90s, which actually showed that, in fact, this Fokker-Planck equation, or similarly this marginal distribution, is itself a gradient flow, but over the space of probability measures. So it's following steepest descent of some functional, in this case, the Kalbach-Leibler divergence. So it's steepest descent, but steepest with respect to the geometry, a specific geometry on probability measures, which is the Wasserstein geometry arising from optimal transport. So from this connection, this is where we're actually trying to really bridge optimization with sampling by trying to apply optimization methods over the space of measures. And in fact, the tools that are employed here are related to optimization over curve spaces. So Melanie, for example, mentioned some work in this direction, and the tools are actually quite similar since they've been developed at a fairly high level. So only say curvature bounds. And so we know, for example, the space of probability measures is positively curved. And so anything that works for positively curved geodesic spaces, so we need to have like shortest path in there, actually will work. And so you can try to apply all the toolbox of convex optimization to speed up sampling. So this there's many directions to exploit this, and this is what we're doing this semester. So one successful way of doing this is to use particle methods that try to directly discretize this gradient flow. SVGD is one of them, and you can see that the trajectories of those interacting particles are actually quite different than if they were just independent stochastic differential equations with drift. So what are we doing? Well, we have the usual format for a Simon's program. We started with a boot camp where we put enforced quantitative organization, since we're bringing people from a variety of communities, optimization, sampling, PDEs, theoretical computer science, analysis, calculus of variations. And so we had 5 days, 5 themes that you can see here. And we have 3 workshops. So one has already happened in September, and it was mostly focused on sampling and exactly the discussion that I just mentioned. So either stochastic differential equation discretizations or particle methods. There's a second workshop happening next week, which will focus on the links with PDEs and particle methods. So similar approach, but maybe with a center of mass that's a little more towards these particle methods rather than the stochastic diffusions. And the last workshop happening in December will mostly focus on the optimization aspect. So optimization over some manifolds that actually have algebraic structures and exploit quantitative symmetry. We also have a bunch of weekly activities. You can see the list of working groups that are happening. There's 6 of them, so we are keeping quite busy, and there's some really interesting things that are coming out. All right, so I think my time is up, so I thank you for your attention.
Thank you, Philippe. Our next speaker is Frederick Eberhardt from Caltech.
Thank you. Let me get set up.
Frederick sets up.
Can you see that well?
Yes.
Shall I start?
Yes.
Yes.
Thank you all for having me. I am one of the organizers of the Causality program for the spring semester. We're hoping to bring together a whole variety of different people from many different fields to have a broad look at causality, and in particular to bring some of the insights from theoretical computer science to causal inference. Of course, as you all know, causation enters into all sorts of questions in the sciences. I think in many domains, actually, understanding the causal relations within a system is the ultimate goal of that sort of scientific research. So in particular in neuroscience or climate science, I think that's what we're after in trying to discover the causal relations. But also then causality plays an important role in understanding what happens when we intervene on a system, so that we not only predict what happens to a system, but that we can predict when we change a system what will happen. And so in that sense, causality or an understanding of the causal relations is important for medicine, for policy, for education, and of course in the political sciences. There's a further more, well, it's a very old aspect where causal reasoning plays an important role, but which has got to become more important recently, is that causality often underlies our attribution of blame and responsibility as well. So this is, of course, important in the law and for attributing moral responsibility, but I think more recently it's become incredibly important in understanding questions in explainable AI or in fairness and in fault detection. So here we then have to ask about whether we can automate these sorts of notions and in what sense causality plays a central role to our understanding of fairness or to our understanding of explainability. Okay, so the challenges, of course, for causal inference these days are vast. So in particular, there's this question of how do we handle extraordinarily large amounts of data, say from the Human Connectome project for measures of the brain, or from the Sloan Sky Digital Survey for astronomical data. Similarly, you might ask about data that comes from social media. And in order to address that these sorts of vast quantities of data, we need methods for causality that are not going to just work for 10 or 15 variables, but for hundreds or thousands of variables. And we need to change the kind of methods that we have now to be robust to fluctuations in the data, to be applicable to a large variety of different data sets, and then to really be able to integrate different types of data so that we can use images, that we can integrate time series, that we can mix discrete and continuous data and still talk about causal inference. I think we have a fairly good understanding of how to do causal inference in relatively small settings, but to really scale to this sort of data that we have available now requires rather different techniques, and I think rather different approaches that we might get some insight from theoretical computer science. The other aspect I think that is of great interest is that it is actually in some domains possible to perform enormous numbers of experiments. So in gene regulatory networks, we can now do an enormous amount of experiments at the same time or in sequence. We can automate the experiments. Similarly, when we think about posting ads, there can be all sorts of experiments one can, at least under certain circumstances, run on social media as well. And so if we're going to run an enormous number of experiments to discover the causal relations, then of course we have to ask ourselves about how we might optimally sequence experiments, how we choose our intervention targets, and how we can efficiently integrate findings from many, many different experiments that are run automatically, where we can't somehow handcraft or stitch together the results in different ways. So the program we have brings together people from many different domains to address these sorts of questions, and we've built the program for next spring around 3 workshops that we've set up. So we'll start, like all the programs, with a boot camp in the first or second week of the program, but then we'll have 3 different workshops that focus on different aspects of causal inference. One in February for learning from interventions, the second in March on algorithmic aspects of causal inference, and the third, that is quite different, in April on the relation between results in causal inference and quantum physics. So in the first workshop, we're aiming at this sort of question of how do we do the combinatorics of different experiments and how can we optimize sequences of experiments, while the second workshop focuses more on questions of robust causal inference. How can we give robust estimates of the causal predictions that we make, and what sort of error bounds can we compute, and how do we compute those sorts of error bounds efficiently? The third workshop on the relationship between quantum physics and statistical causal models is really an effort to explore somewhat new ground, where in many ways the causal models that we build these days don't work very well or can't be extended naturally into quantum physics. So the question is, how can that be done? And there have been initial approaches that raise very interesting questions about the relation between results in quantum physics and what sort of inferences one might draw about causal models with latent variables in statistics. And so that's something that we want to explore in this extra workshop that's at the end of April. At the moment, we're very busy setting everything up for the coming semester. If you look on the website, you can see all the people who will be joining the program. And I'm very much looking forward to an exciting semester up in Berkeley, hopefully all in person. Thank you.
Thank you, Frederick. Our next speaker is Vasilis Ziganis. Any questions for Frederick while Vasilis sets up? All right.
Don't see any.
All right. Next speaker, Vasilis.
Great, thanks, Marcel. So yeah, so the sister semester for the spring is learning and games, and this is the list of co-organizers. So the main topic of learning and games is to study fundamental problems at the intersection of learning theory, game theory, and mechanism design. Some of the motivating reasons why we thought this semester was timely are the following. First, machine learning algorithms are currently ingesting data that are either owned or generated by self-interested parties, and many of those parties might even be benefiting from the outcomes of those algorithms. Examples include credit scoring. And so those machine learning algorithms are susceptible to manipulation, and this needs to be taken care of when we design machine learning systems. Another motivating reason why these 3 research areas need to be studied together is that nowadays machine learning algorithms are being used to optimize economic systems or learn how to play optimally in strategic scenarios. One leading example is auction platforms, where machine learning algorithms are being used to optimize reserve prices or other parameters of the system, and the participants themselves are using learning algorithms to learn how to play optimally. A third example is the fact that as machine learning is being deployed in critical systems, then it's becoming more prone to adversarial attacks, and game theory can give a nice lens to how to deal with such adversarial attacks from a theoretic view. And finally, we've seen in the last few years many novel machine learning frameworks that are being phrased as finding the equilibrium of a game as opposed to the solution of an optimization problem. And so there, again, the intersection of learning theory and game theory is very relevant. There's already been several successes at the intersection of these 3 fields. For instance, the online learning theory view of large-scale training can be viewed as a topic at the intersection of learning theory and zero-sum games. We've seen generative adversarial networks, which is like a game theoretic view of generative modeling. There has been a lot of successes around game playing with the development of multi-agent reinforcement learning algorithms for Go or Texas Hold'em, and even the deployment of manipulation-proof credit scoring markets. For example, a very nice work has been recently published on deploying a manipulation-proof credit scoring algorithm in Kenya, where manipulation was really a key issue. So driven by all of these scenarios, the semester is going to study research topics in several areas. For example, min-max optimization, multi-agent reinforcement learning, dynamical systems and learning in games, behavioral game theory, econometrics in games, and learning and mechanism design. The semester will host 3 workshops. The first workshop is on adversarial approaches in machine learning, and primarily focusing on all of these novel frameworks that I mentioned, where the machine learning model, or the model that we're trying to learn, is formulated as an equilibrium of a game as opposed to the minimizer of an objective function. An example application areas of this is generative adversarial networks or adversarial robustness. The second workshop is learning in the presence of strategic behavior, where we will focus on topics where the learning system needs to understand incentives and deal with incentives and be designed so that incentives won't deteriorate the performance of the system. It will touch topics such as humans in the loop or mechanism design and learning. And the final workshop will be on multi-agent reinforcement learning, where we'll try to understand how to develop or analyze reinforcement learning algorithms where there are multiple agents simultaneously interacting and the actions of one agent affects the utility of another. So that's it. These are the long-term participants. If you want to check out and reach out. Thank you very much.
Thank you, Vasilis. Our next speaker is Vinod Vaikuntanathan from MIT.
Hi, Vinod. Thank you.
Hi, Prasad. Hi, me. Let me try to share my screen. Can everyone see?
We can see it. It's just not in presentation mode.
Oh, good. Okay, all right. Okay. I can go, right?
Sure thing. Go ahead.
Okay, good. So hello, everyone. It's good to be here. I'm going to talk about the program on lattices, algorithms, complexity, and cryptography that we organized in spring 2020. And we had a virtual short 1 week long reunion in summer 2021, like a few months ago. And we are planning for a sort of a extended reunion in person, hopefully in summer 2022, and I'm really looking forward to it. So the organizers of the program were Shafi, who you know, myself, Khotekwi, Daniela Michancho, and Oded Regeb. So let me sort of say a few words about what the program was about. The start of the show was this mathematical object called lattices. And this is what it looks like in 2 dimensions. So this is really a set of, you have 2 vectors, you take all integer linear combinations of these 2 vectors, that gives you a lattice. And this guy seems to, turns out to be a really amazing, very powerful mathematical object. Has been studied for many, many years, in fact, centuries. So this guy is Kepler, apparently. Somebody drew a picture, I have to take their word for it. So in mathematics, this lattice has come up in the question of sphere packing, which is really, you have 100 oranges and you have a crate. What is the best way to sort of arrange the oranges? What's the densest packing you can get? And at least in some dimensions, in fact, I think even 24 dimensions, the densest lattice packing is you take a lattice and you put the balls, the oranges on the lattice points, on the vertices of the lattice. So this was studied for a long time in mathematics, and this is really like the beginning of it in number theory and algebraic number theory. This shows up all the time. In computer science, lattices sort of came up really with the with the groundbreaking work of Lenstra and Lobash in the 1980s, where they showed how lattices are connected to integer programming. They actually showed a singly exponential. They actually showed an algorithm for integer programming, which is exponential, but only in the dimension, independent of the number of bits you need to write down the numbers, etc. And that was very influential. It's used really all over the place. In cryptography, which is sort of what the main focus of the program was, lattices again turn out to be a very powerful object. Cryptography and lattices have a sort of a love-hate relationship. In the 1980s and 90s, lattice algorithms, in particular the LLL or Lenstra and Lobash algorithm, was used to break encryption schemes, break crypto systems. And then in the mid-90s, things turned around, and with the work of Miklos Aitai, we found out that they can be our friends. You can actually use lattices to build encryption systems, digital signature schemes, and all sorts of wonderful cryptographic objects. So they have several very appealing features that make them unique from the perspective of cryptography. For one, in the hopefully near future, and maybe Umesh can say more about it, we'll have a quantum computer. And then, thanks or no thanks to Peter Shor, much of the cryptography that we use today on the internet is broken. It's just gone because of Shor's algorithm. So we in cryptography have been thinking about how to fix this, how to live in this potential post-quantum world. And lattices give us a way to rebuild essentially the entire cryptography in a way that even quantum computers cannot break, as far as we know, right? And in fact, NIST, the National Institute of Standards and Technology, has been running a competition to standardize post-quantum secure encryption and digital signature schemes, and lattices are the leading candidate. And I think they will standardize, they'll finish the standardization process in sometime the next year or two. And for all you know, your email and your internet communications will be protected with lattices in a decade. Okay, so that's how important these things are. They're also good for many other things other than post-quantum security. Lattices give us essentially the only way to compute on encrypted data. So this is a way to sort of encrypt your emails, your images, or whatever you store on the cloud, while still enabling the cloud to actually run algorithms inside the encrypted data without actually opening the encryption, right? So there's this, okay, nice. So there's this object called fully homomorphic encryption, which enables computing on data without seeing it, without opening a box. And lattices are essentially the only way we know how to do it. The other sort of feature of the program from spring 2020 was that it was co-located with the quantum program, quantum wave and computing program. And that was sort of, that was a great thing. That was really a wonderful thing for, I believe, for both programs. Because lattices and quantum computing, as I think I already hinted, have a very sort of productive relationship with each other. For example, a recent sort of breakthrough, a groundbreaking sort of development in quantum computing is an answer to the question of whether you can, you as a classical algorithm can verify the correctness of arbitrary quantum computations. The answer is yes, as shown by Urmila Mahadev in her work a few years ago. And the answer kind of comes from lattice-based cryptography. So to sum up, our program is studies lattices with a particular focus on cryptography. We had a boot camp as usual, 3 workshops, and we actually had an additional special joint workshop with the quantum program on quantum cryptanalysis of post-quantum cryptography. So the point is, given that the internet is probably going to run on lattice-based cryptography in a decade or two, we have to understand how really secure lattices are, both against classical algorithms as well as quantum algorithms. The point of the workshop was to explore this issue. So let me sort of just say a few technical highlights that came from the program. There was this wonderful result by Jain, Lin, and Sahai that constructs this object called program obfuscation. So homomorphic encryption is encrypting data, program obfuscation is encrypting programs in a nutshell. and they showed how to do it from standard cryptographic assumptions, one of which is sort of lattice assumptions. As I mentioned before, there were productive interactions with the quantum program, including this mini workshop. There was a very impactful reading group called Quantum for Dummies that people organized. This was intended for sort of lattice people who don't know quantum to actually like learn the bracket symbol, starting with that, and really kind of learn the basics of quantum computing. And a lot of results that happened that came up in the last year and a half, can actually be traced back to this workshop and to the participants in this, not workshop, this reading group, and participants in this reading group, including these two results. I think all the people in this belonging to these two results were actually in the program, and they were attendees and speakers at this reading group. Lots of other results. We had to cut the program short in the middle of March in person, and then we continued the program for the whole duration virtually. I think that actually put a damper in the amount of productivity that people had, but it's great to see, despite that, what people did, and really the community came together to keep the program going despite the adversarial situation. So technical highlights. There were lots of sort of, really the pandemic brought the community together. So in some sense, I don't know how much of sort of the non-technical highlights would have happened without the pandemic. So thank you very much, I suppose. So we really bonded over the adversity. So this is a hike that we did, I think March 13, the day before Gavin Newsom announced that, well, look, let's all go home and stay in place order, right? That's what it's called. So we had fun as much as we could. This is another sort of fun thing that Amy actually and Shafi put together. Is a program called Cooks in Theory, where we would come together and we'd really cook together. That was a lot of fun. We continued it well beyond the end of the program, and I don't know if it would have happened without the pandemic. So again, I suppose thank you. But anyway, so to sum up, I'm actually really looking forward to being back in person for the extended reunion, and hopefully having even more fun, in person than online. So thank you.
Thank you, Vinod. Our final talk today would be by our own Umesh Vazirani on the quantum wave computing. Excellent.
Okay. Thank you, and thanks Vinod for a wonderful presentation. So I'm going to, my presentation is going to be quite minimalistic compared to yours, and I'm really glad that you went before me. And you covered a lot of important points about the two programs being co-located together. I'll speak a little bit to that soon. So the quantum wave in computing program was co-organized by Andrew Childs, Ignacio Serra, Thomas Videk, and myself. And there were, if you look at quantum computing, there, obviously it fits into this, this template of the Simons Institute. It's highly interdisciplinary, and at the moment there are two very big open questions in the field. Well, there are three. One is how quickly can we scale up the size of quantum computers, and then the other two questions are, well, once we get there, what are the algorithms that are really going to be useful, and what are the applications of those algorithms? And as far as we can tell, the two important, the two really important application areas would be quantum simulation and quantum chemistry. And in both of these areas, you need really both a computer science and physics chemistry, to come together. And this is exactly what happened in this program. So one of the most fundamental problems in quantum chemistry is the so-called electronic structure problem, where you're given the locations of the nuclei of the atoms in a molecule, and you want to understand what's the energy of that system. Because if you can minimize that energy, you would understand the structure of that entire molecule. And so there was this collaboration that developed between two chemists, Brian O'Gorman and James Whitfield, and two computer scientists, Bill Pfefferman and Sandy Irani. And they spent the semester sort of understanding each other, and then over the course of that period, they even after the COVID shutdown, they continued to work and figured out that in fact this problem, if you want to study it in a formal sense, it's QMA hard, even in a particular single fixed particle basis. So this really informs what kind of algorithms you can look for. Would there need to be heuristics and so on once you move to quantum algorithms? There was another such collaboration that came about in a very interesting way. So when you do quantum simulation, many of the quantum many-body systems you want to simulate have this property that they are, you might be looking at one-dimensional or two-dimensional or three-dimensional systems where you're with a regular lattice structure, and your interactions are all the same, independent of which atoms are or which spins are interacting with each other. And so now, what would n be then? Because you can specify the interaction using a constant amount of information. And so to specify the actual problem, you don't need, what should n be? So Ignacio Cirac, one of the organizers of the program, made a suggestion that in fact, n should be the precision to which you need to compute the ground energy. And so this was something that had been proposed in one of our discussions, and then Dorit Aronov and Sandy Irani sort of decided to take this up, and they worked at it, and there's a beautiful result that they gave, which is that the complexity of this problem is doubly exponential, and so they were able to characterize it completely. Now there was on the quantum algorithms front, I've highlighted some of these results that came about, both because they are interesting, but also because they illustrate the kind of interaction that went about in these programs. So there was a whiteboard seminar. We used to call it the brainstorming seminar that Andrew Childs gave, and that sort of led to two different results, which dealt with two different sort of big open questions. One was property testing, quantum property testing for a sparse graph. So there's this well-developed theory about property testing, where you're given some graph and you can only access it. You don't even get to access most of the graph. You can only access small pieces of the graph. Like you can ask, is there an edge between vertex U and vertex V? And the question is, can you actually figure out this graph property? Is it connected? What's the eigenvalue of the graph, etc. By probing only a small part of the graph. And so Andrew Childs and Andras Gillian were able to give an answer to this. They were able to show that you can get exponential speedups using quantum algorithms. The same brainstorming session actually led to another collaboration between Andras Gillian and me, and this had to do with quantum annealing and its complexity. Now, quantum annealing is this was, for example, the algorithm that was being used by this company D-Wave, and one of the properties of the Hamiltonians that they were using was that they were stochastic, and in fact this has been a long-standing open question. Stochastic Hamiltonians were considered to be sort of somewhat classical, in some rough sense, because they could be solved by quantum Monte Carlo in practice. And so the question was, Would you even get exponential speedups with these kinds of algorithms in quantum annealing? And so we were able to answer this question in the affirmative. And actually, this was a sort of an unexpected answer that you could get exponential speedups in this model. Now, as Vinod mentioned, this program was co-located with the Lattices program. And there are these beautiful connections between the two areas already in terms of the validation and verification of quantum computers. Specifically Urmila's results, but there's a lot of results in this in that intersection, which seem to suggest that this co-location was really it was a very nice occasion. And I think at the end of the day, there were just a very large number of results, and there was a real feeling that this co-location of the two programs has really started a new era in post-quantum cryptography. Sorry, the double quantum was not intended here. In particular, there was this very nice collaboration that started between these four people: Bartusek, Colatangelo, Corana, Ma. Andrea Colatangelo was working in quantum, on the quantum side. Dakshita Khurana was working purely on the classical side, and then Bartoshik and Ma were somewhere in the middle. And they started a very intense collaboration, where they actually managed to solve these two major open questions, having to do with quantum multi-party computation and whether you can obtain one-way functions from oblivious whether you can obtain oblivious transfer from one-way functions. Actually, the second result was independently done by Grillo, Lin, and Vinod, where Grillo was, he does quantum, and the other two obviously were from the Lattice program. So this probably shows the level of activity between the two groups and how intense it was. I think that the feeling so I've seen a number of programs at the Simons Institute, and the sentiments expressed by the participants in terms of the level of the meeting of minds between the two, and the level at which they felt that they had really, at least on the quantum side, that they felt that they had internalized the classical cryptography notions from lattices, that this went to a very different level, and it completely transcended the program itself and specific results that they were working on. And so in this sense also, it was quite a unique semester and program. And of course, as Vinod said, this our program was interrupted halfway through by COVID, and I think that that created adversity always creates bonds, and I think it created a different level of bonding within the programs as well as between them. So it was really quite an event for us.
Thanks, Umesh. Thank you for the introduction. Any questions for Umesh or Vinod?
I don't see any. David, did you want to ask a question? No? Okay. Go ahead, Prasad.
All right. Thank you to all the program organizers for sharing their experience organizing the program or the expectations of upcoming programs. And thanks to all the fellows for sharing their results and our industrial partners. It's been quite an intense day, fully packed. what we missed by meeting in person, I hope we made up with it, the intensity, and hopefully the virtual networking sessions helped at least a little bit. I, for one, hope that we'll do this in person in the coming years. If there are fellows or program organizers that people would like to connect with after the event, please check our website for contact details or contact Amy and she'll help you get in touch with any researchers or fellows at the Institute. We look forward to receiving feedback about the event in the post-event survey. And finally, before we close, we want to encourage you to stay in touch with us, either with our monthly newsletter you can subscribe to, our website, or our YouTube channel, where a lot of our talks are recorded and posted. And if you have time right now, please do join us on the Gather Town gathering for a final meetup to say bye. Thank you for all the industrial partners for their partnership, and see you all next year.
Thank you, everyone. Thank you, Prasad.
Thank you.